So, in the last class, we discussed about the conditions of interference, and here we will apply that idea to derive an expression for the fringe width. So, fringe width is defined as the distance between two successive bright spots or between two successive dark spots. Two successive dark spots or between two successive bright spots. So, this is the O is the foot of the perpendicular dropped from the source S on the screen. And P is the point at distance y from the foot of the perpendicular. And if we write this distance S1, S2 as d, then this half of this will be OM. So, OM is d by 2, and similarly this half is ON, that is also d by 2, and this distance between the cardboard and the screen be capital D. Now, we can apply say Pythagoras theorem to the triangles S1 PM and S2 PN. So, Pythagoras theorem gives S1P square is equal to S1M square plus MP square is equal to S1M is nothing but D square plus MP is Y minus D by 2 whole square. This is say equation 1. Similarly, your S2P square is equal to S2N square plus NP square is equal to D square plus Y plus D by 2 whole square. This is equation 2. But our intention is to find the path difference S2P minus S1P. So, S1P is now, suppose you take D square common, it is 1 plus y minus d by 2 by d, then whole square, whole to the power half is equal to d, then 1 plus y minus d by 2 by d whole square, then to the power half. From experiments, it has been found that y is of the order of millimeter, while d is of the order of centimeter. So, since y is much less than d, comma, we can use binomial expansion. One plus x to the power n nearly equal to 1 plus nx, provided x is much less than 1. So, here it is satisfying that condition. So, S1p is now nearly equal to d, then 1 plus n is half y minus d by 2 by capital D whole square. If you open it, it becomes d plus 1 by 2 d, d square is there, so d cancels, that is y minus d by 2 whole square. So, in the same way, similarly, from equation 2, we can write S2p is equal to d plus 1 by 2d, then y plus d by 2 whole square, equation number 4. So, now path difference is S2p minus S1p. So, that can be found from equations 3 and 4. So, delta is equal to path difference is equal to S2p minus S1p is equal to S2p is here d plus 1 by 2d y plus d by 2 whole square minus d minus 1 by 2d y minus d by 2 whole square. So, that is 1 by 2d, then y plus d by 2 whole square minus y minus d by 2 whole square, that is 1 by 2d. It is 4ab, 4 y d by 2, that is y d by d. So, this is your path difference. Then from the conditions of interference, we know that when the path difference is even multiple of lambda by 2, there is formation of bright spots on the screen, and if it is odd multiple of lambda by 2, then dark spots are formed. So, here what we do is for the nth bright spot, because many bright spots are there. So, we will label them. I will show in the next figure. O, at O there is S1O is equal to S2O. So, path difference is 0. So, there is a 0th bright spot. Then on either side there will be first bright spot, then second bright spot, like that. So, let us say that for the nth bright spot, on the screen, comma, delta is equal to 2n lambda by 2 is equal to y n d by d. So, y n indicates the distance from the point just where y n is equal to distance of the nth bright spot, from the point O. O is the foot of the perpendicular dropped from S on the screen. So, from this what you get? Y n is equal to n lambda capital D by small d. So, y n plus 1 will be n plus 1 into lambda d by d. So, now, here will be 0th bright spot, then suppose it is y n 1, 2, 3, 4, 5, y 5. So, y 6 will be this one, that is y n plus 1. So, in between there will be dark spots. So, we can write it as 6th bright spot, then 5th bright spot, then 4th bright spot, and 3rd bright spot, 2nd bright spot, 1st bright spot, and on this side also there are there. So, beta, that is the distance between two nearest bright spots. So, beta is equal to y n plus 1 minus y n, that is n plus 1 minus n into lambda d by d. So, n cancels, you get d lambda by small d. So, this is the expression for beta. So, you get the expression beta is equal to d lambda by d, and from this it follows that beta is proportional to d when lambda and small d are kept constants. So, beta proportional to lambda when d and small d kept constants, beta is proportional to 1 by d. That means, when the separation decreases, then beta increases. when d and lambda are kept constants. So, this is about the derivation of the fringe widths. In the examinations, problems are asked. So, like find the distance between the first dark spot and the second bright spot. As you see from the second figure, first dark spot is this one. It is at a distance of beta by 2. Then there is beta. So, beta plus beta by 2, that is 3 beta by 2. So, this type of things are asked sometimes in the examinations. So, one has to be careful. Then we come to the phenomenon of diffraction. Diffraction is the bending of light around an obstacle, is called diffraction. That means it clearly says that light does not travel in straight lines, and these are of two types actually. One is Fresnel type, the other is Fraunhofer type. Fresnel type, the source and the screen are at finite distance from the obstacle. Here source and the screen are effectively at infinite distance from the obstacle. So, in the +2 syllabus only Fraunhofer diffraction due to a single slit is there. There are also theories in higher classes, Fraunhofer diffraction due to double slit, due to n slits, which is called grating. So, those things are there, but here we will just discuss the diffraction due to a single slit. So, any slit, however small may be, can be regarded as made out of many points. That means, large number of secondary waves emerge from a single slit, and these secondary waves, they superpose on each other to produce the diffraction effect, which as we have discussed, it is bending. So, let us see what happens here. So, by means of a convex lens, say L1, rays are made parallel. So, these are the rays. So, they proceed and rays are parallel means effectively the source is at infinity. Although it is in the laboratory, but due to the lens L1 having focal length f1, they are made parallel, rays are made parallel. So, these are the plane wave fronts. And there is a slit. Actually, slit is small, but we show it enlarged to explain the thing. So, this is the slit, and the slit width is A, suppose. And this slit consists of many small sources. So, each source is producing waves which expand with time in all directions. So, what you do is you take another convex lens L2. This is a screen and those which move horizontally parallel to each other, they superpose to converge near the point P0, not exactly P0. So, this is this hill type of thing represents the intensity pattern. Intensity is maximum here and it is called principal maximum. Principal maximum. Then what the other things are observed? Suppose some inclined way the rays travel in some inclined way parallel to each other, making same angle theta with this one. They converge to another point on the screen. So, this is called say B1. B1 means bright, first secondary maximum. Then this is B2, second secondary maximum, and B3. So, others are having less intensity, so they cannot be seen or they cannot be observed. And this is your D1, first dark spot, this is D2. Similarly, here D1, D2, then D3, the dark spots. So, this is the experimental arrangement by which you can observe the diffraction due to a single slit, and this is the intensity pattern. Intensity pattern due to Fraunhofer diffraction. due to a single slit. So, now Fraunhofer diffraction due to a single slit. Then the question is how to explain this type of intensity pattern, or what is the theory behind it. Actually, theory is a little bit complicated. So, we will quote the final result. We will quote the final result and discuss from that. So, explanation. It can be shown that I theta is equal to I 0 into sine square alpha by alpha square, where I 0 is equal to maximum intensity. I 0 is equal to maximum intensity and I theta is equal to intensity due to waves moving in directions making theta with the horizontal, theta with the horizontal. And what is alpha? Alpha is equal to pi by lambda a sin theta. So, to make just an idea about alpha, you see the slit is there. So, this is for theta is equal to 0 directions, and for some theta value the rays are like this. So, these are the points inside the single slit. If you drop a perpendicular on this second line, then you can see that this plus this angle is 90 degree and this plus this is 90 degree. So, this angle is theta and this is your A. So, sin theta in this right angle triangle, sin theta is equal to, this is say x by A. So, x is equal to A sin theta, and what is x? X is equal to path difference. X is equal to path difference between the two extreme rays. Extreme rays means there are many points. From each point such directions are there, as shown in this figure. So, we have taken only the extreme ones, this one and last one we have taken. So, that is the difference is path difference is your this one, that is A sin theta, which leads to the phase difference.